Welcome to the 5th lecture of system level programming. Today we will continue with the example that we started off with, and before we talk about semaphores, we will go through the code one more time just to make sure that we are all up to date on the code. So what we created was an example where we had an array numbers to sum up and also a variable sum of all numbers. We have producer threads that write numbers into this numbers to sum up, and we had a variable sum of all numbers where the consumer threads read the values from this array and add this into this sum of all numbers. So what we have here is now two threads, the producer thread, which produces a lot of numbers, and then there's a lot of locking code here already, then stores this number to store down here into this array. That's basically what happens. So all of this other stuff here is just maintaining the program safety. With locking, with checks whether we are doing everything right, whether the entry is available. So the actual thing we wanted to do was just number to store and store it in this array. And then we wanted down here this consumer to basically iterate over that loop, over that array all the time. And whenever it finds an entry that is filled with data, then it should take that entry, sum it up, and reset that entry to -1. Down here we had our main function, which created 10 producers and 10 consumers. We have we initialized the array here. We had the producer threads that we create with pthread create, and then the consumer threads that we create with pthread create, and then pthread join on all the producer threads. And afterwards we check, is the array really empty, or is there still something left? If there's nothing left for the consumers, then the consumers are cancelled in this example. At the end, we print the number that we have observed overall, and that's basically the full program. I will also check whether there's anything I should not overlook on the Menti, but I will rather defer the questions to a bit later in the lecture when we have started with the with all the content. Okay, so let's go through this program again. We used mutexes and condition variables here to protect this code. And what we did there was we first added some numbers just to count how many free spots are there, how many consumable spots are there, which made it convenient for us to work with that. Just to know whether we can currently store a new number into this array or not. The main thing that makes this thread safe are these two locks here. The numbers to sum up lock and the sum of all numbers lock. They are the locks for these resources. And that's always how I would start with such a locking example. I look at what are the resources and then add a lock for each of these resources. So let's see, how do we use these locks? Great idea. We just look up where these locks are used and see that or if we would not have the locks yet, we would look up this resource, of course, and we can see that it's accessed down here, and that means we have to lock the mutex before. And we do this actually pretty early on up here, because we are working here with the condition variables that must be protected with the same lock. The condition variables refer to the same mutex, so they must be protected with the same lock. So that means we lock from here to down here, and then we have the same in the consumer. We lock this from here to down here, although we only have a few lines of code in the middle. That, of course, is a lot of locking. We would like to lock less code maybe, but it depends on what the program does here. And with the condition variables, yeah, we need to lock them as well. Oh, now I opened the wrong view on Menti. Let me just check that I have the right Menti open. And someone in the chat says the email reminders are great. Yes, but I also don't think every time of the email reminder, especially if I'm in a hurry, then the TOG online mail sending takes another 5 minutes that sometimes I don't have. So let's continue with this example. Mutex is quite complicated, right? With the condition variables and so on. It's a lot of code. Maybe we can make that more simple. There are some questions in the Menti about A3 and about CMake that I won't answer. These are more suitable for the Discord. Yeah, I will just skip a few questions just so that we can make some progress. At the end of the lecture, if we still have time, you can still ask these questions. There's also a question on semaphores already. I will explain semaphores now, so I hope that question will also be resolved with the explanation. I'm not taking the question now, therefore. Okay, let's do that. Let's get rid of these mutexes and these condition variables and replace them with semaphores. And the last time we replaced some logs, we checked how do they work. Sem_wait. So how does sem_wait work? We need to include semaphore header file. Okay, let's do that right away. Great. First part is already done. So the next part, sem_wait, sem_try_wait, sem_timed_wait. Don't use these. If you use try_wait, that usually indicates that you don't have a proper locking situation here, and that it would be more reasonable to rethink what your program does. Especially if you have a loop where you try_wait until you have the lock, that totally doesn't make any sense. Timed_wait, similar, if you have a loop where you try and try again, usually that doesn't make any sense. There are very, very few situations where timed_wait or try_wait actually makes sense. We don't have any of these in the practicals. Let's read a bit about these functions. So we have sem_wait here. And I also should just do one more thing here on my side with the VS Code. Yes, that's better. Okay. Sem_wait decrements, that means locks, the semaphore pointed to by sem. And I would be a bit careful here about locks, because a semaphore is not the same as a mutex. The semaphore pointed to by sem. Okay, so it decrements the semaphore. A semaphore is a counting variable. A counting variable sounds useful. If the semaphore's value is greater than 0, then the decrement proceeds and the function returns immediately. Okay. Let's think about our toilet example again. We had this nice example with a public toilet and a toilet cabin, and let's assume we protect this with a semaphore and we initialize the semaphore counter to 2. Is it then thread safe? The toilet cabin? It's not thread safe. Although we use the semaphore, it's not thread safe, because if 2 people can enter it at the same time, then you still have a race condition in the toilet. So well, that's a bit of a problem. Someone writes in the chat, must the semaphore variable be locked? No, actually the semaphore variable doesn't have to be locked. But we will see in a second what we need to do. If the semaphore currently has the value 0, then the call blocks until either it becomes possible to perform the decrement or a signal handler interrupts the call. So I think as a first step, we can do the following. We can use semT to replace this. semT, numbers to sum up lock. Now we need to use this other initializer because I didn't see anything about, well, we need to check seminit. There is no initializer for that, right? Okay, so we have to use this initializer function. Let's do that. Initializes the unnamed semaphore at the address pointed to by sem. Okay. Great. So the other arguments p shared, a lot about p shared indicates whether the semaphore is shared between the threads of a process or between processes. I'm fine if it's 0, then it's shared between threads of a process. That's fine. And we also have to provide, so let's look at this, semT, a pointer, a reference to semT, and a value. The value argument specifies the initial value for the semaphore. And we had already in the lecture that a semaphore that is initialized with a value of 1, where the value can only be 1 or 0, has a very similar behavior to a mutex. So let's do that. Seminit, we pass our numbers to sum up lock. We don't want it to be process shared, and we want it to have a value of 1. Like a mutex, now it can be decremented by 1 thread, then it's at 0, every other thread will block, and then the one thread that has decremented it can increment it later on, so it can unlock it later on, and with that our semaphore will behave exactly the same as a mutex. Just that we have to replace now all the calls to pthread mutex lock with semWait. Let's do that. Why not use a mutex then? When I learned about mutexes and condition variables and semaphores, I did not understand mutexes and condition variables first. But I understood semaphores, and then I only used semaphores for everything. I want to show you that semaphores are very powerful, and which of these locking mechanisms you understand best now. That's of course individual to every person. So if you get along with mutexes very well and with condition variables, then you will be able to solve basically all the challenges with mutexes and condition variables. If you figure out that semaphores are more intuitive for you, then I want to give you this opportunity to work with semaphores. So let's do that. We replaced mutex lock with semWait, and for we need the counterpart for unlock, and that is semPost. So semPost increments the semaphore pointed to by sem. If the semaphore's value becomes greater than 0, then another process or thread blocked in a semWait call will be woken up and proceed to lock the semaphore. It always says lock here, but I really like the notion of increment and decrement because it's not really a lock. Okay, so let's replace that with semPost. Okay. Now we replaced all the mutexes. So let's see what happens if we compile this. Let's try this. I will just compile this. Okay. Oh, a lot of errors, or warnings at least. So what does it not like? Ah, yes, the condition variables, they don't know about semaphores. Okay. Maybe I can remove the condition variables for now. Maybe I can comment them out and the program might still work. Because condition variables should only make things faster. They shouldn't be necessary for the control flow here. because we have anyways our while loop here, and we only leave the while loop if we got some consumable spot here or some free spot in the other case. So we will remove these condition variables, and let's see whether it now compiles with pure errors. Okay, sempost from incompatible pointer type. Ah yes, it's still a mutex t. Of course, we did not replace that part. Mutex t, it has to be a sem t. And also no pthread mutex initializer. We need to initialize also this mutex. Well, mutex, now it's a semaphore, but it behaves exactly the same in this example because we initialize it to 1 and we only decrement it then in one thread, and then this thread also increments it. So let's take a look at, yeah, now it compiles without any problems. We can run this. Doesn't look too good, huh? Why not use a mutex then? We already used the mutex, right? We already solved the entire example with mutexes. So let's check what our code would be doing now. It will lock this semaphore, and then while the numbers to summer free spots is 0, it would stay in this loop. This is a volatile variable, so it can be changed by the other threads as well. Then we decrement this, then we go in here, store the number, increase the number of consumable spots, and break out of this loop. Here we have our sem wait again. That's a problem. Think about it. What the pthread cont did, it unlocked and locked the mutex again, right? If we think about the implementation of pthread cont, what it internally did was, internally does pthread mutex unlock, then it does some yield or something, maybe a get yield, it allows some other thread to run, and then it does a pthread mutex lock. And now we don't have this anymore, so this loop is locked all the time. And that's problematic. In the chat, someone says, I think the problem might be that if the semaphore is higher than 1, like 20 threads run to some shared variable and access it asynchronous. So we have to combine it with a mutex. Yes, or with a semaphore that has a value of 1 or 0. So usually you combine these two things. So let's see what we can do here. So this logic here is now missing because we removed this cont wait call. So maybe let's just add this manually. Here's our workaround. And I'm not saying that this is beautiful in any way, but it works, right? We could do the same with mutexes. We could also do the mutex unlock here and then mutex lock, and it would work without semaphores and without condition variables. But I want to show you just that this simple semaphore case works. I will just use sempost, then semwait. And I do the same in the other location where we had the same loop, because we need to unlock, otherwise no process can change this variable, right? If we don't unlock this for a short time at least. Let's see whether this is already enough. Oh yeah, this works. And this should be thread safe because we just replaced the mutex with semwait, and works still the same. Now this is not really beautiful. I don't like this while loop here. And what we said was that a semaphore is also a counter. So why not make this here a semaphore and this here also a semaphore? So we make these semaphores. We have to initialize them to 0 and to number array size, but they are we don't need this condition variables anymore. They can go away. And we can just initialize them to the right values. Let's copy that down here into the main function. we will initialize them with SemInit again. Number to sum up free spots. Well, free spots in the beginning we have exactly array size free spots. And then here we have consumable spots. In the beginning we don't have any consumable spots. And that's very nice. Now we replace the counter. We have to provide 0 for, it's not P shared, right? Not process shared. And now we have these counters as semaphores. And this gives us a big advantage, as you will see in a second. How do we use them? Well, we now can't increment and decrement anymore. And we also can't use these while loops anymore. What do we do instead? Well, let's see. Up here, we now can check whether or not there are free spots with a semaphore, and this will be thread safe. We won't pass this line of code unless there is a free spot. So we don't even have to lock up the numbers to sum up array. We just use our semaphore for that. Very good. So that means that once we reach this line of code, we know that there is a free spot, and that means we can remove all of this code. Great. We can remove this code because the semWait up here already decremented this. Removing more code. Very nice. And we also don't have to lock this iteration over the array, do we? We could lock here now because the array size stays the same, so there's nothing to lock here. So we lock here and we know that we will find an entry. Maybe it's still safer to lock here because we iterate over the array. Maybe someone releases an entry while we are iterating over it. It's safer to lock up here because the array could change in the meantime while we are iterating over it. So, and then we can unlock down here, but we know that this loop is only run through a single time, and we definitely have found a free spot then to store the number. So we can remove all of this part, and this is not a plus plus anymore, but now a sem post, because a sem post is an increment. Very nice. So the code now looks much more simple. Okay. So I'm seeing a YouTube warning here, and it says the bitrate of the current audio is 0. I hope that you can still hear me and everything is fine. So I'm a bit confused by the YouTube warning here. Okay. Let's just check some questions on Menti. I think there are 2 questions, and I think they are good to take now. I created 2 threads, both calling printf. Does that mean that standard out is a shared resource and therefore needs to be locked in both threads? No, we consider usually only resources that we have allocated. Standard out, you didn't allocate standard out, so that's fine. Do I need a pthread join for this example? For A2, I'm not sure actually. I didn't look at that. I know that you need some locking mechanisms. That's why I'm explaining them. I would have to check whether you need pthread join, but you already used pthread join, I think, in A1, so that should be not a problem anymore. I expect that everything that you already used should be no problem to use. So this sem post here, we can also move this up now, right? because we know that if we pass this sem wait, we know that there will be a free spot, and we know that we get in this loop, we will find one if where we go into, and we know that we will store the number, and we know that sem post will succeed here. So we can also move up the sem post for the lock, which is nice because then the doorknob, yes, there's a doorknob. So let me try whether I can move this up. A bit more. Now the doorknob should be gone. Okay. Okay, let's see. Then let's also protect the other function with the same mechanism. Again, we don't want to use this while loop anymore. This was super complicated. Let's use the sem wait on exactly this variable. Numbers, consumable spots. We wait for that to be larger than 0. Let me add this comment here. If you are new to Semaphores, then this might make sense. This basically in a thread safe way does while numbers to sum up consumable spots is 0. If this, or let me abbreviate that a bit, while consumable spots is 0. That's basically what this loop does, or this call does, in a thread safe way. So it will wait until there's at least one free spot. If you want to write it like this, wait until greater than 0. That's what this operation does. Could I crop the webcam feed? Yes, but if I do, then I can't point here anymore, and I like pointing at things. So that's why I have this in there. Okay. Great. So we replaced this one. Now we already do the decrement in here. Yeah, this also, it does not only wait until it's greater than 0, but it waits until it's 0 and then it decrements. I do like pointers, yes, of course. Then let's see. We have our numbers to sum up block here. We iterate over the array, we find the number to sum up, and here we increment the semaphore again. We again can move this one up because we don't use the array afterwards anymore. And we need to also post the free spots because we just freed one of these spots. Great. Same program, simpler logic. I like it. Let's run this. Oh, wait a second. This is not thread safe anymore. Okay, where did we mess up? Let's check. So we have our numbers to sum up block. We have our sum of all numbers block, and they are initialized to 1. That's good. Then we have our free spots. It's initialized to the size of this array. Should also be fine. We have 16 arrays in 16 spots in there. So if the thread's decremented every time, then we should have 16 threads can write in there, and then the 17th attempt would block. Sounds good. Then we have here our sum numbers to sum up block. We iterate over the array, we post it here. Number to sum up consumable spots is then posted. So that means that this one now can proceed, because in the beginning this one will not be able to proceed. Then it will lock the array. It will read the number from the array, and then it will also post this one. Interesting. So where did we add our locking error? Maybe we should also, maybe this is also important. So we should probably lock over the iteration over the array. So we shouldn't iterate over the array without locking it. And this loop down here actually now is not so beautiful, right? It's not very beautiful because we are still iterating over this and checking whether everything is done. What else could we do? If all the producer threads are done, maybe we can make this even more beautiful with another semaphore. And this semaphore says, or with a condition variable, that would also work. With a condition variable that says that there's nothing more in this array. So they iterate over this array. Oh, I know what I messed up. So here, of course, I need to break out of this loop. Otherwise, they would we would not have proper locking, right? That's of course one of the problems. But down here, this loop, I still don't like this loop. Let's see whether the locking problem, I think the locking problem that we had was the missing break. I somehow lost that break while changing the code. Oh, this feels like 65,000 locks for one resource. Actually, yes, so this looks good again. Number looks stable. Actually, you see that only one is a lock. The others are no locks. If it has the underscore lock at the end, then it's a lock. Otherwise, it's not a lock. It's a synchronization mechanism. Similar as a condition variable. A condition variable is not a lock. But semaphores basically play both roles here. They now play the role of the condition variable in a much more elegant way. And at the same time, they also play the role of the mutex, so you can use it as a lock. There's a question in the chat. Well, can we decide whether we want to use semaphores or mutexes? I think so, yes. In general, you will be able to choose that. I think for A2, you can also solve that with mutexes or with semaphores. It might be necessary to use semaphores in one or the other place because the solution with condition variables still had this loop in there and it was not the most beautiful solution. With semaphores, it looks more elegant. So it might be necessary to use semaphores at least for some of these counting cases. Okay. Let's add one more element here. So I know how to solve this with a condition variable. So we joined all the producer threads. So we know that no more elements can be produced. So I want to wait for a condition variable. I want to wait for an event, and this event is consumers have no more work. I'm not sure whether this works like that, because the problem is now the consumers, if they have no more work, and they signal that. It might be that it's in between and the producers would still produce new values after that. So I want the consumers to only signal that once there's really nothing anymore. So maybe we need to signal in both directions, of course. Let's do that. So we have a variable which says volatile size t is array empty, or let's say do array empty check. And in the beginning it's 0. And the consumers will not use that variable most of the time. But sometimes they will. If do array empty check, then they will do this check. Then they will check, but at the same time it's difficult, right? Because they will be stuck in there if they don't have anything to do anymore. So are we not overcomplicating things in there? Yes, the thing that I want to do is I want to get rid of this loop because I don't like this loop. And I'm thinking now how we can get rid of this loop. So the consumers, once they are done, they will all queue up in here. One solution, of course, is, I can show you that as well, is semGetValue. SemGetValue takes a semaphore pointed to by sem and places the integer value that it currently has in sval. Let's see what this does. Probably we can do that. While semGetValue, and we now use the same counter variables as before. We have our consumable spots and the free spots, semGetValue. Okay, so let's do that while 1. And we need to create 2 variables, consumable spots. I don't know, I initialize it to some value. It doesn't matter because I'm overwriting it right away anyway. And address of consumable spots. And then we use semGetValue with the free spots. And now we have the values of these semaphores. If free spots equals number array size and consumable spots equals 0, then we know they are done, right? If there's everything, if the producer's already terminated and if all the spots are free, then we know that we're done. And I also I just saw how we can make this more beautiful afterwards. But this is a good first step. So we can use this while loop now. And now we only have one while loop, not a while loop and a for loop. That might be a bit simple. And we break out of the loop here. Let's see whether this still works or whether we screwed it up again. Okay, so this incompatible pointer type. Oh, this one's an int pointer. An int pointer. Aren't we busy waiting here? Yes, absolutely. But we were also busy waiting before, but no one noticed. So yes, let's try this. I'm just trying now whether this works. It looks okay. So how can we change this? Think about it. At the end of the program, there are no more producers, right? That means that the semaphore, which value will this semaphore have? We are just checking this here. Free spot semaphore will have the value 16. So we can make a very, very nice mechanism here to wait until all the consumers are done. We just create a loop, size t, starting at I going up to number array size, plus I. And now we wait for 3 spots. 16 times. And now it's much nicer. So what do? We know that at the end of the program, when we joined all the producers, there are no more producers. There should be, when all the consumers are done, there should be 16 of these free spots. If there aren't, then not all consumers are done yet. So that means if we wait 16 times on this semaphore, if we can do that, then we are certainly done. Then we are sure that all the consumers are done as well, and then we can kill them with cancel. So let's try whether that works. Oh, very nice. Works. And that's our semaphore example. Okay, so let's see. I really like that this example got so much easier now. It's just the same weight here, same weight there, same post, same weight. All this complicated stuff with the mutexes and the loops and the condition variables. All of them gone. So, okay, so what do we have here? So someone is trying to recruit you for Amazon, it seems. So of course that's a good opportunity, but I hope that you first do operating systems before joining any companies. But of course, interesting opportunities are always a good thing. What am I even watching here? Well, some system level programming class, I guess. So, are semaphores safer against race conditions than condition variables? Semaphores are inherently thread safe. So if you, meaning that both the post and the wait operation are thread safe. So you don't have to acquire some additional mutex or semaphore to make that operation thread safe as you have for condition variables. So in that sense, maybe you could say that, but the programs that you write, they are not more or less thread safe if you use the one or the other. It's just a matter of taste, basically, whether you prefer semaphores or condition variables. Are you uploading the code? Yes. So in the last YouTube video, you found a description. Below the video where the link was in there, and I will also do the same here. After the video ended, I will upload the file and I will add the link to the video description. Is there any catch to using semaphores, or could I just use semaphores only in H2 without worrying? I think so. I think the example should be solvable with semaphores only. In the end, semaphores are the most powerful of these concepts, and you can implement mutexes with semaphores. You could do that, right? You could write a wrapper function which you call pthread mutex lock and internally just use a semaphore. And you can do the same also for condition variables, as we've just seen, right? So you can implement exactly the same logic with semaphores. Semaphores are the most generic and most powerful concept. There's maybe one problem of semaphores. Semaphores do less thinking for you. For a mutex, if you try to unlock a mutex that you haven't locked, the mutex will say that's not okay, you can't do that, and it will throw an error, or maybe it's undefined behavior. But what it doesn't do is it doesn't increment the value to some nonsense value for a lock. But for a semaphore, if you have a bug in your program and you post too often, then the semaphore value will increase and increase, and the lock will have no effect anymore because you are not using it as a lock anymore. So the semaphore, it's easier to break things if you are not confident that you have understood the concept of locking yet. But Personally, for me, semaphores were the easiest concept to understand, and I used semaphores then for a year before I really understood how to use condition variables in a nice way. Okay. Well, that message is not from me, and that's not a valid email address. Actually, you would have to write IAIK there, not student. Or you can also use my student mail address, but then you have to omit the Daniel dot at the beginning. So, I mean, we still have a lot of time, right? We still have more than an hour. We will talk about A3 now. Do we have to free enemies and heroes in A2 since they never get allocated but never free? I don't think we check with the wall grind for this example. Can we use mutexes and semaphores in A2? Of course. There are no limitations on that. How do you initialize pthread const instructs? Let me show that. I will show that to you. And so you want to create a struct. Let's say we have a struct here, struct my logs, and I will add some variables in here, semT my sem, then pthread const my cond, and pthread mutex t my mutex, and we will now initialize them. Okay, what does it say? Oh yeah, okay. Why do I have a spell checker enabled here? Very weird. Okay. And, yeah, I need a semicolon here. Okay, now I have a struct. Great. Let's initialize them. And for that, let me just copy over that struct down here. I like to see the struct while I initialize it. So, like this. Okay, and then it's seminit address of my logs dot my sem 0, maybe 1, I don't know. And then my logs wait a second, my logs struct my logs. Well, I probably don't have the syntax at hand anymore. How C should do that. Do I have to write it here? No, that's also weird. Let me do it like this. Type def. I like to type def structs. My log struct, and now I will say my log struct my logs. Okay, that's better. I prefer that, and then we can use my logs. I'm still confused. My logs. Why? Oh, my semaphore. Yes. Address off. Why is it? This is just spell. What? Can I disable this spell checker, please? Where is this? So disable. Yes, better, because it's confusing me if it shows weird underlined variables, although everything is fine, right? So yes, this is looking better. I like type defs. I must say, I find them very nice to define things. Also, type defs. This is also something. If you want to work with function pointers, you can make a type def for function pointers. Type def. You want a function pointer, a fun pointer. And you can make this a type def, and then you can say, well, this should be a function pointer that takes a void pointer and returns a void pointer. And here's my type def for the function pointer, which is really nice because now I can just say fun pointer f, and this is a function pointer. And now casting and everything is very nice because you can just cast to this type def. Oh, why didn't we know that before? But again, the syntax here is a bit weird because the type def name has to go where the variable name would go, right? Okay, someone did that already in A1. Yes, you can definitely do that. Let me just rearrange things here a bit. Okay, function pointer so that we also show this type def. And we will also initialize the other parts, pthread mutex init, my mutex, and there we have to pass a second value, the attributes, and then we have the pthread cond init. Okay, and there we also have to pass my cond like this. Does it need more values? Well, let's check pthread cond init. I always have to look things up. It also wants attributes. Okay, so we can pass a 0 there. And checking things in the man page often is a good idea. This is how you initialize semaphores, mutexes, and conditional variables in structs. So a question, will the next lectures be registered soon in the timetable? So I think so there are lectures registered in the timetable, so in TOG Online, and I think I also entered a date for today, but I only did that yesterday, so you would have to reload your calendar to see it. But for the remaining lecture dates, I think we can stick to the regular schedule, so I think it will always be the same day and the same time for the remainder of the semester. But in the beginning, we needed to get started early to have this content for A2. If I would have this lecture, this was lecture, or this, we are still in half of the lecture, lecture 5, and we will cover A3 now in a second. If I would have had this lecture 5 in week 5 of the semester, then it would have been 3 weeks after the deadline for A2, and it would have been no use for you. So that's why we have some of that grouped together at the beginning, so that we can start with the practicals early on and also cover all the content. Okay, so yeah, so this part is basically done. I want to show you one next example, and for that, let me just briefly check whether I have some code prepared for that. Yes, I have, and that will allow me to be a bit faster with what I want to do. Okay, so I will create a new file here. I will basically duplicate this file with thread.c, and I will copy, paste, thread copy, rename this into secfold.c, and we can remove a lot of things here because we don't need most of the stuff. And maybe a question while I do that for the chat. I guess most of you know secfolds. So what do you think of secfolds? Are secfolds great? Are secfolds something to worry about? And this is now a content for A3, yes. What about secfolds? If you have a segfault in a program, is that a problem for the system? What if I have many segfaults? Let's say I write a program that segfaults all the time. Is that good or bad? So I want to do the following. Let's start with a simple program, get character. Very simple program. And there are some comments in the chat, and they say sometimes good for debugging. You do something wrong in your program if you have segfaults. Maybe that's true, but maybe in some cases it's also exactly what I want to do. Something to worry about. You should avoid them for memory's sake. Yes, you are right. You're not wrong, but you will see that segfaults are not always a bad thing. So let's call GCC on this one. So we have our segfault segfault.c. I want to run this one, segfault here, and I want to also have a second terminal because I want to show you some stuff here. Okay, let's see. I run segfault here, so I will make this one very narrow. Okay, yeah, maybe like this. Okay, and here I will open a tool. So I don't need this sidebar actually. Can I hide the sidebar? Only hide the sidebar. I can make it at least more narrow. Okay, and here I will open htop. So, okay, this is a lot of programs. So let's search for segfault. Here's my, with htop, I can search for my program with F4, filter, segfault, and now I can see what this one does. I can see the PID, I can see the user, priority, okay, virt, res, share. We have to figure out what those are. CPU, and here's memory. CPU, it doesn't use any CPU right now, it doesn't use any memory, and here's how I started it. Okay, that's good. Well, let's do something more. There's also cut proc, and now I want to read something from this segfault program, some information about this segfault program from the procfs. And for that, there's the tool PID of segfault. My program is called segfault, PID of segfault. Okay, that's my PID. So what I can do is I can say now cut proc, and with these backtick operators, you can just write PID of segfault here, and it will insert the PID into this command line now. Very convenient. And actually, I just want to use ls now. I want to see what things we can look up for this program. We can look up command line. Oh, and let's take a look at that command line. Cut. This is how we started the program. Let's see. I want to check whether that's actually true. Segfault 123. It's now called segfault 123, as you can see. Segfault 123. Okay, interesting. So command line has the command line arguments. What else do we have? We have environ. What is that? Environ. Let's take a look at this. Oh, the environment variables. Oof, a lot of stuff. PID of. Let's check what else we have. I want to get this line again. It auto completes this. Let's run this one again. ls. So what else do we want to see? We want to see what is maps and what is mem. That's interesting. Let's take a look at mem. Oh, we can't look at mem. That's the memory of the process that we could map. We will learn about that. There will be a system called, a function called mmap that we can use to map memory into our address space, or you can also read from that as a file. If you use sudo, you have the permissions to do that. Let's take a look at maps. Oh, maps, what is that? So let's zoom a bit out here. So this is a bit, yeah, we need to make this a bit larger so that we can actually see this properly. No, still not large enough. Let me make this window a bit larger so that we can fit this in the larger font size in there. Yes, that's fine. Maps, what does this do? Okay, so this is printing me some, that looks like some addresses. Okay, so I want to combine some things here. Maybe I can change my program a bit. Maybe I can go in my program and say I want to print the address of the main function. I want to print the address of main. Okay. Let's do that. Let's compile that and we run that. Segfault thing. Okay, here we can see the address of the main function. Let's again this window up. Okay. Interesting. So that's the address of the main function. Okay. But that address doesn't look anything like this. Oh, but also we called this before. We have to call this again because we recompiled and restarted the program. And now, oh, this address here and this address, yeah, these addresses here, they look very similar. So this is 562D0C4EB, and here it's EC. Okay, this is EC, yes, here. This must be in this memory region. So let's see, what do we see about this memory region? Here it says it's readable. R is readable. It's W, probably writable. X, executable. And P, well, it's present. It's there. So we always see here read, write, executable. And then we see here where in this file is this. That's the offset in this file. So this is the file that I'm opening, and this is where this location maps to. So I could look in the file, and at this offset and this offset in the file, and I would find the main function. Should we take a look at that? Let's take a look at that. Let's try object dump on segfault. Okay, we are trying to figure out how these binaries work. We are just looking at addresses. So these are addresses, and we are trying to figure out how a computer works. So we print this main address, and we want to see now whether 169 plus this offset is really the place where we find the main function in this segfault binary. So that was 100. So 1 with all zeros. So that's basically here the start. We can see that that's the start. But then it was 169. 169. Yes, that's the address of the main function. That's great. So we understand what this does, right? So this maps file tells us where things are in the binary and what addresses they get when the program is executed. So this is interesting. If we run the program again, wait a second, we always get a different address. Look at this. The address is always different. Okay, I want to use another function here that I know. Watch -n, and I will pass 0.1 here. And I will watch this call here. So let's see what this one does. We don't need assembly for A3, but we do need to understand a bit about how programs work, how binaries work. So let's run this one, and it says, oh, no such file, or that's not working as expected. So how can we do that? Let's maybe run it like this. Does this work? No, it says number expected. So what can we do? We can store this PID. Let's do it like this. We store this PID into a variable. PID is PID of segfault. And then we say cut PID maps. Let's see, does that one work? Also doesn't work. So we need to improve our bash skills here. So let's see. Watch. We need to. I thought it was working like this. So let's try it step by step. PID of segfault. If I run this, yes, then I see the PID. Okay, but the problem is that I have to pass this on to the cut proc pid maps. I thought it should work like this, but let's try it maybe like this. Maybe this works. Okay. Also doesn't work. I have an idea. I will write a small script. Cut maps. And here I will do exactly that. Cut proc PID of segfault maps. There's a question in the chat saying if we have a semaphore with values 3, that means up to 3 threads can execute the locked code at the same time. There's a misunderstanding here. If 3 threads can execute the locked, if 3 threads can execute something, access some resource at the same time, then it's not locked code. Even if you use a semaphore, if you are not making sure that only a single thread can access the resource, then it is not locked code. Or how exactly does it work when the semaphore has a value of 1 greater than 1? It doesn't lock. It's not thread safe. It's not thread safe if the value is greater than 1. You can use that for counting. We did that in the example that I've shown you before. But you still have to protect it with a value, with a semaphore that has a value of 1 or 0 if only one thread can access the resource. Only then it is really locked. Yes. So here we have our code in there. Okay, and then we try, well, we have to give this execute permissions, watch -n01 cut maps. Yeah. And if I terminate the program now, yeah, then it's gone. Okay. And now I could, so you see that every time I run this, I get a different address. The addresses change all the time, and all of them, not just those up here, but all of these addresses, all of them change all the time. We get completely new addresses all the time. So addresses. Addresses are pointers in RAM, right? They point into RAM. So maybe let me close this terminal for a second. I want to try something out. I have a global variable here. Int global, and I initialize it to a value of 4. Then I will print the address of the global variable, and then I will increment the global variable, get character, and so the question on Menti is whether we only have the lecture on Mondays now and nothing else. Yes, that's correct. I mean, there's the question hours also on top of that, but mainly it's just the lecture on Mondays. So, and I also want to print the value of this one. So if I dereference this pointer, then it has the value. Oh, it's actually, I used an integer here. That's super ugly. Let's make it a size t. I don't like integers. Size t is much better. And then we also print that here. We something like this. Let's run this and see what happens. So we run this. We dereference the address. It has the value 4. Now, which value does it have? Write it in the chat if you know what value it has. And then I will print it, of course. Right? So we had initialized it to a value 4. We call it global ++ Now we print it. And 5. Correct. Correct. 5. Great. Okay, now I will change one more thing, and I will open a second terminal again, and we run this program multiple times. Okay, so we have enough space here. So I will run this one time here and one time here. Okay. Ooh. I increase the value on the left side. Now I increase the value on the right side. Okay. Now on the left side, which value will it print? Five again. 5 and 5. That makes sense, right? Ah, yeah, of course. These are different addresses. Is it important that they are different addresses? Let's do one more trick. So someone already mentioned in the chat that we should do that. We compile it with static now. Now let's see what happens now. Segfault and segfault, and we can see that, it's the same address. Ooh. Okay, let's see what happens. I increase it on the left side and I increase it on the right side. Which value do they print? Oh, and now people are not so sure about this anymore. Some say 5 and 5, 5 and 6, 6 and 6. So if it's the same address and they are both incrementing the same address, I used get character, so it was basically synchronized by hand, right? So they incremented not at the same time. So I would understand 6 and 6 because you say, well, it's the same address, so both increments went to the same address, then both now must print 6. I understand that. I also understand 5 and 5, but we will get to that in a second. So let's see what happens. 5 and 5. Okay, that's interesting. So they have the same address. Oh, but okay, I mean, it's the same address, it's the same value printed at the same address, right? So it's the same. Let's try that with a different, example. So let's add int argc here and then some character argv, character pointer argv. And what we do is we have to pass an argument, then argument 1, and we say that global equals this one. If you don't know strtool, then that's string to unsigned long. You can again check this in the man page because there is a man page also for that. Great. We need to include standard lib for that. Include standard lib.h. Okay. Then we compile this. It doesn't like that. Too few arguments. Yes, we should have checked the man page. Oh, it needs a pointer, an end pointer, and a base. Okay. We don't need the end pointer in this case. And here it also says, it's always good to check the man page. And then we have our end pointer here somewhere. If end pointer is not null, then it stores the address of the first invalid character. Can be quite useful. We don't need it. We pass null there. And the base is 10. We want to we want to enter a decimal character. So we compile this. We run this with segfault, and now they will run it with five. Okay. Segfault, let's say 3. Okay. Okay, this is now interesting. So we are starting this program twice. We get the same address. Now this one wrote 5 to that address. This one wrote 3 to that address. And we learned in ESP, we learned that a pointer is basically just an index, a number in RAM, right? In this large array that is the memory, the main memory of our system, the RAM. So let's see. We run this. We increment it. Which value do we see now on the left side? We see 6. And on the right side, 4. It seems like although they are working on exactly the same address, they have nothing to do with each other. How is that possible? Yes, it's using virtual memory and not directly physical addresses in the RAM. So this is important to see that programs can't interfere with each other just because they have the same addresses here, because these addresses have no meaning outside of the process. They only have a meaning inside the process. In the chat it says you cannot directly modify RAM. Well, they do modify RAM, but this address will be translated to an actual hardware address. So this address for now doesn't mean anything. It's just a number within a program. Okay, that's interesting. So if this is just a number within a program, let's maybe go one step back and let's take a look at these maps again. I want to take a look at these maps again. And we had this. This is also very useful if you are not used to Linux terminals. Press Ctrl R and then search for whatever you wanted to search for, a command that you have entered before, and then you can use that to search for that command again. And we can see that our program, oh, it's actually quite short here, right? Yes. So with static, the program got shorter. So we don't need all this large terminal now. Smaller terminal is enough now. We can see that, yes. So these are the valid regions in our program. So what happens if we use fork? So let me do like this, and this goes here. Just arranging my windows here so that I can also show you the example that I wanted to show you. So we now understand that apparently these addresses are not really real. They are, yeah, someone calls them virtual, not real addresses, unreal addresses. Okay, virtual addresses, yeah, that's also what I would say, but we learn more about that in operating systems. For now, we just need to know programs are apparently, if we run them twice, if we run 2 processes, they are independent of each other. Think about C++ classes. If you have member variables in classes, you can increment them independently and they won't influence each other. And it's the same here with the processes. You remember this analogy, process, program, and thread is like object relates to the class and that relates to method. So what do? We will, we will start off with a pointer. Let's try a volatile character pointer. I will use a character pointer now. I like character pointers. And this character pointer here, I can use a local variable for that. And what I want to do is I want to dereference it and see what happens. So let's see. I can close this one. I don't need this one anymore. Let's compile this. And does anyone know what happens? Of course, you know what happens. Let me just find where the chat was. Here it is. Segfault. Yes, I really like segfaults because segfaults are so, yeah, interesting. So many things you can do with segfaults. Okay. Segfaults. Okay, that's not so nice. I wanted to basically print something after the segfault. Can I do that? Can I printf something like this? Address P is invalid or something, or is valid or something. And then I pass this address there. Let's try. If I compile that, will it work? No, it's still segfaults. Damn it. How can we solve that? Well, maybe. So you know this situation where you are not the one to blame, but someone else is to blame. Maybe we can do something similar. Do something similar here as well. So maybe not let us do the segfault, but someone else. Yes, exactly. I like the idea from the chat. Well, let's call it fork. And then we have solved the problem, right? Fork and segfault. Oh no, now we get multiple segfaults. Okay, so we have to be a bit careful there. And also I want to check, do we have any processes still lying around? No, okay. Kill all is nice if you want to check whether there's still one process left around. Let our child do the deed. Yes, let's do that. Okay, fork. We need to get the return value of fork, PID, fork. And then if the PID equals 0, then we dereference the address and return 0. Otherwise, we print that. That's okay. We need to do something more here, right? Because if we do it like this, then I mean that's not useful. So at least we are not crashing. We are printing the message. That's already good. But we need to wait here. Can we get? Is there something like wait man3 wait? Why not? So let's check out this man page. What does it say? Wait for a child process to stop or terminate. Exactly what we wanted to do. So what do we need? We need to include this sys/wait header. Okay. And what does it say? Wait. The wait and wait PID function shall obtain status information pertaining to one of the callers. Well, wait, let me make this a bit smaller so that I can properly read it. Okay. One of the caller's child processes. The wait function obtains status information for process termination from any child processes. The wait PID function obtains status information. I don't need any status information actually. Wait function shall cause the calling thread to become blocked until status information generated by child process termination is made available, or until delivery of the signal. Okay, a lot of information. We would have to read that more carefully before we use that. Sometimes the POSIX standard has these nice examples down here. Yeah, fork, wait PID. Interesting. Okay, so this would be an example where we can copy something from. Here again, this some handling What else do we have here? Fork and okay. A lot of examples, lots of code. I think I will just use the wait call here. And apparently it wants to give us some return value. I would have to look up what the return value is here, right? So let's for now just hide this terminal. Use the wait function. Oh, that's not the wait function. Wait function with some return value. It has some return value. And the return value, what did it say? Which value does it have? Well, type, it's an integer pointer, so int redval, and we pass the address here. So we wait. Yes. Oh, there's a comment in the chat. You said the child does not know the parent, but get PPID returns the parent PID. Yes, of course, there will be system calls, but only with these system calls the child can look up the parent, but sometimes also not. Maybe get PPID won't return a PID in all cases. I don't know. Or maybe PPID, you might not have implemented that in your operating system. Then you also don't have this. So let's say wait, and then we say let's printf that value, redval. And I want to print the redval. It's a integer, so let's print this as a decimal number integer. And we don't need this one now, but I want to run this. Oh, I want to run this maybe now one time with Okay, so this is a weird redval. Oh, that's a very weird redval. That's a very weird redval. Some number. I'm not sure what I would do with that. Let's try something else. What if we don't have a segfault here? Let's try what wait does then. Still not so nice. Redval. Maybe we should do this. Maybe we should initialize it. Maybe that's a problem. No, still not. Wait a second. Here it says, oh, of course, we are not. That's a stupid mistake, but that happens. We should, of course, print the. Yeah, that makes a lot more sense. We should get rid of our warnings. The warnings here are not so nice. So let's check the man pages here for fork. We need to include some headers. It's not good to leave warnings in the code, right? So let's get rid of them. Void pointer address. It's unused. Yes, for now it's unused, but we will use it again. And now the redval is 0 as we expected, right? That's this one. Let's dereference address. What happens then? 139. I'm sure you've seen 139 already in some test system, in some coding in ESP or SAP, because that's the return value, the signal that Linux uses to tell you that it was a segfault. 139 is a segfault, 0 is fine. So if redval is 0, then let's print something. Let's print address P. We already had that here. Address P is valid. Okay. And then we also want to, maybe we want to call, we want to maybe do some tricks here. I will show you some of the tricks now. So we will take a look at some codes that you can use to rewind lines in the terminal. And I will use %s for that, or I will use %s for that. And what I do here is I want to distinguish two cases now. I want to distinguish valid addresses and invalid addresses, just to have some more convenient printing. Yeah, I need to define some constant for that. Define invalid 0. Okay, that's my last state is valid. So the last address I say was valid. And basically what I do then is, if the last state was invalid, then I want to print a new line, and otherwise I want to do something more fancy. I want to rewind the line, because otherwise I will print really a lot, and then that's the code to rewind a line. Okay, I hope I got this one right, because these codes, I mean, I always have to look them up how they work exactly. So we rewind the line, and then we print whether the address is valid. I also will use, yes, I should use f-flush because I don't have a new line there, and then printf doesn't use f-flush. Also, the last state is valid in this example now. Okay. If it's not valid, I also want to print something, and basically the same stuff. Okay, like this. Yeah, but I want to print that it's invalid, and then also say here that it's invalid, and I only want to print that if it's valid, the last one. Okay, great. Let's try what happens if we run this. Yeah, of course. We don't have any loop or anything, so we need to create a loop here, while 1. And this is something you have to be very careful about. And I hope I didn't introduce any mistake in my code now, because calling fork in a while 1 loop is a very fast way to get your computer to not be able to continue anymore. So I hope that this is fine. And maybe just for starters, I will add a sleep statement here, just to be sure that I'm not doing anything stupid. Where is invalid? It doesn't do anything else? Oh, it's printing all the time. Oh, okay. So maybe let's... of course. Let's skip this part at first. So we will just use a regular printf. Printf address is valid, and we will just print the address and comment out this line for now, and also same down here, so that we see that our program is actually working. Okay. Yes, we forgot the comma here and here. Let's run this again. Yes. Okay, so the program is working, and we are getting seg faults 1 per second. Our program is getting seg faults all the time. And let's again check with, okay, with this one, we can check, is there any process still running? No, there isn't. So that's fine. But we actually don't want to check the null pointer all the time. We want to check different addresses. So let's say plus 4096, or maybe a different address. Let's maybe start at not at address 0, but I want to start at address of main, and I will cast that to a volatile character pointer. And then I will also increase by just one byte. I want to see where the address becomes invalid then later on. Okay. Yes, this works. We can see which addresses are valid. Also another question here. How can an address be invalid if a pointer just points into RAM? Then every pointer has to be valid. It only is possible that if a pointer is actually a virtual address that doesn't necessarily map to physical memory, that then it is valid or not. If it maps to the physical memory, it's valid. If it doesn't, then it's not. So we now increase the address, but this is too slow. Let's have more segfaults per second. And I'm adding a yield here just to be sure. And I'll check the man page for scat yield. For that, we need to include scat h. We yield the processor, causes the calling thread to relinquish the CPU. It means that some other thread gets to compute next. We don't want to keep the CPU busy all the time. Whoa, this is interesting. This is a lot of segfaults per second. And you said we shouldn't have too many segfaults in our program? I'm having hundreds of segfaults in my program now. The question is, does it do anything useful? Okay, we can open a second terminal. Oh, this is a lot of, and we will again watch this. Okay, so 48. Oh yeah. So it should go until 497. Oh, then it continues here until 4C. Oh, invalid. Very nice. So our program works. Very interesting. Okay, so I have an idea. Why would they want addresses to be invalid? Great question. Let me do this. Look at this address here. How much is this in let's say in gigabytes or megabytes? Let's write this here in a comment. One hex character, if you translate a hex character into binary, then for instance, F is 1111. E is, for instance, 1110. We have, for instance, 8, that's 1000, right? So one hex character has 4 bits. So let's take this address here. Okay, this one. Let's see. So this one has 4 plus 4 for the next one, plus 4 for the next one, another 4 for the next one, another 4, another more and more. And I'm just counting how many bits we are needing here. And the 5, I know that a 5 is something like 101, so we need another 3 bits at least here. Okay. Let's sum that up. So this is 16, this is another 16, and this is 15. 15. Okay, so that's 32, and that's plus 15, that's 47. 47 bits. We know that 2 to the 10 byte is 1 kilobyte. Because 2 to the 10 is 1024. That's 1 kilobyte. And there's a very simple rule that you can follow here. 2 to the 20 byte is 1024 kilobyte. That's 1 megabyte. And then 2 to the 30 byte is 1 gigabyte, and then 2 to the 40 byte is 1 terabyte. Whoa, 1 terabyte of memory? I have a pretty fancy computer here, because that means, because of this address, where this address is, it becomes clear that 2 to the 47 bytes are 128 terabytes. I have 128 terabytes of RAM in my computer, apparently. Let's check htop whether that's true. It says no, it's not true. It only is 62.7 gigabytes, so 64 gigabytes. How does that add up? 128 terabytes. How can I have an address? How can I have my main function at 128 terabytes if I only have 64 gigabytes? That's off by a factor of 2000. The address is 2000 times higher than I have memory in my system. Why do you want to have invalid addresses? Because most of these addresses cannot be valid because I don't have enough RAM for that. If I have a 64-bit computer, I can't have 2 to the 64 bytes of memory. So most of them have to be invalid. Does that answer the question? If not, just ask again. And we have seen here that before, let's scroll up. Oh, we have to scroll up far. We can't scroll up far enough. That's unfortunate. We have seen that this jump was actually not at a border of 1 byte, but actually the last few bytes had a certain value. Let's maybe try this again with a larger step size, because the step size, so look at this. So here, that's interesting. So let's run this again, and we can see that the step from valid to invalid always has these last 3 hex characters set to 0. Let me try that again and also open at the same time again this proc maps thing. I want to see that one again. Yeah, so maybe. Okay, so I'm adding a get char here. I want to have some time to look at that. Okay, what do we have? This is again the variant without static. I would prefer the variant with static just because the addresses were shorter, right? So you see the addresses are shorter if I compile it with static. The addresses here don't mean anything really, right? They are just virtual addresses. So what you can see is, the stack is always up here. There's a heap. And here's our program. The code, the read-only data, writable data, all of that is mapped. Interesting. So you can also see here that the borders between these areas always have the last 3 digits 0. There's no single case where the last 3 digits are not 0. What does compiling with static do exactly? Compiling with static means that we don't want to link shared libraries. I can show that again. If I compile it without static, we will have a lot of shared libraries, like the libc will be linked as a shared library. We have the Linux loader is linked as a shared library. So they are all so these are all then shared libraries in shared memory that are used. That's in principle that's efficient, so that's a good thing. But with static, this is all just compiled into the binary. So you now have duplicated binary code. The compiler duplicates the code from all these libraries into your program, and just the code that you need, of course. And then, of course, you don't need the shared libraries anymore. And another effect, the side effect of static is actually that Linux disables a feature called address space layout randomization when compiling with static. It disables that at least for the binary and for the data, for the BSS segment, and for the heap. And because it disables that, we get very predictable, very low addresses here. Yes, static binaries would then be larger as well. I would expect that. At least if you use several library functions, then it would have to be larger. Okay, so we now saw that we don't have to care about all the offsets. That's interesting. We only have to care about those where the last 3 hex digits are 0. So we can just iterate over the addresses in this size here, plus 1000. And let's see what happens. And maybe also we want to make sure that we start at 0 and not at the main function. And I want to print now. All these addresses, and I want to remove the get character because I don't need it anymore. And also the get yield. We can do more segfaults per second. That's a lot of segfaults per second. And you can see that some regions will be valid, right? Was it with static? Yes. Okay, let's run this, and we can again check with proc maps at the same time which addresses should be valid. Let's check PID. Here we can see some. Okay, that was interesting. So we had, oh no, that's still invalid. Okay, no, never mind. Let's call PID of segfault. We want to check which PIDs we have, and we will take maybe this one here, because the other one is changing, right? Yeah, this one stays the same. That's the parent process. So we will watch, cut, proc, and now with the PID maps. And it should say valid at an address where the last 5 digits are 0. Oh, that's very soon. That's very soon. 3F for valid. Yes, there the valid addresses were just very few valid addresses, and then it's all invalid again. Okay. And the next region would then be at DC9. And so we are getting a lot of segfaults per second. Every line is a segfault. And it's no problem. The system is totally fine with that. Why did they tell us in ESP that we should avoid segfaults? Well, of course, if you write a program normally, then you don't want segfaults. But in this case, we want to probe which addresses are valid and which are invalid. And with that, we can do that. Okay, let me try one more thing. We have 10 minutes left. And I want to try one more thing. I want to go a bit into Malloc, and let me just check whether I can just show you this example here. Yes, I can just show you this one. This is really nice. I prepared a small program here, very small program, and this one uses Malloc. So what does it do? It says size is 0. What is it used for to see? Okay, it's used to count at the end. Okay, while one we iterate through this loop. Okay, and we are allocating in this loop. We have another loop. We always allocate 1024 times Malloc with 1 gigabyte. Oh, 1 gigabyte. Whoa, that's a lot, right? That's 1024 times 1024 times 1024. That's 1 gigabyte. In the chat before, someone said, "Isn't that gigabyte?" Yes, but in computer science, if you say gigabyte or megabyte, you mean the power of 2 version. No one in computer science would use gigabyte to distinguish those, right? Sometimes you do, but gigabyte is in computer science is almost always the power of 2 variant. So what do? We Malloc. Oh, yes. We learned in ESP here. best practice. Check for null. Right? We learned that in ESP. And that's important, right? We don't want our program to have bugs, so that's why we do that. Oh yeah, so it totally makes sense that people taught that in the HTL, especially in electronics, or if you think about hard disks. Hard disks tend to specify the capacity in gigabytes and not GB bytes, but it's a different community, and the capacity then sounds larger than it actually is. So that's why they do that. Best practice. Yes, we check for null. So in my system, you've seen that I have 64 gigabytes of RAM. How often can I call this? Let's just run it like this, right? So I can, let's make this even smaller. Yeah. So 62, yes. Now you can see how much memory is available and how much memory is in use. 7 gigabytes are in use, 7 are available, and I will run this malloc example. And when we see a null pointer, it will print out of memory. And otherwise, it will print how many gigabytes we allocated. I'm not sure why it says terabytes here. Let's just run this with gigabytes, right? We know that it should stop at 57, that would make a lot of sense. So we will just run this with gigabytes. GCC, call this with, this was called malloc C. Okay, let's run this malloc. Whoa. Wait a second, what is going on here? How can I allocate 131,000 gigabytes? Okay, let's try now I know why I had terabytes here. Let's try this with terabytes. How can I allocate 127 terabytes of memory? Ooh. Wait a second. So let me add a get char call here. I want to stop the program here. No, this is not using cloud storage. Let me run this, and now the program is still running. So I allocated 127 terabytes of memory. And look at the memory consumption. It barely changed. So to allocate 128 terabytes of memory, what is this compressed or what? And why does it stop then? That's super weird, right? So that's super weird. So maybe that's something that you have to play around with in A3, right? Because that's not what you would have expected, right? We would have expected that it stops after 60 gigabytes, maybe 57 gigabytes. It stops as soon as there's no more free memory. But apparently, malloc returns 0 long after there is any space left. It still returns, you can see the addresses here, it still returns valid addresses even after 1 terabyte, 2 terabytes. I don't have that much memory, clearly not. But it's still returning valid addresses. That's not what we would have expected, right? And if you would take the questionnaire for A3, there will be questions on malloc. And if you don't try things like this out, you will answer them incorrectly, because that's not what we would have expected to happen. Okay, with that we are at the end of the lecture, and I wish you a lot of fun with playing around with malloc. If you have any questions, I will take them now. So let's see what the Q&A has for us. I think it's a nice cliffhanger here, right? And the solution, you can figure that out on your own. Okay. Is the thing with segfaults important for the assignments? No, but it's, well, for A3 maybe, but it's also important for the understanding for A3 and for, in general, understanding how programs work. And you can't finish a computer science university program without understanding how programs work. I tried a few different approaches in A2, thought everything through, but it doesn't make any difference. Do you have any advice, hints that's actually usable and helps people like me? Open the code side by side. Go through all the cases where a shared resource is accessed. And then try to play this game where you try to reach two different lines, or even the same line in two different tabs. The same line of code where one shared resource is modified while taking all the logs into account. And if you win this game, if you can reach the same line of code from two different threads, that's why we open the two windows, the two tabs, to simulate these two threads. Then you will find the race condition. If you find that you can reach this line, then you have found the race condition. And then you have to fix that one. In A3, can we distinguish between heap and local variables? The addresses are almost the same. Heap and local variables. I would try different heap variables. So heap variables, if you use malloc, not all malloc calls end up on the heap. Some malloc calls will end up on the heap, some will not. I think you can figure out, you can look at the addresses that malloc returns and pass different sizes there. Malloc with 1 byte will return a different address than malloc with a gigabyte. And you can figure out when malloc behaves differently. And then also the variables will look, the variable addresses will look differently, and you should be able to distinguish heap and local variables then. Okay, let's mark this as answered. Menti quiz. I have a Menti quiz also, I think, on this topic, but only for the next, for the start of the next lecture. How can we see how large files get in A3? Or how did you check your RAM usage now in the lecture? I did using htop. You saw the bar at the top where it showed that only 9 gigabytes of my RAM were used, while I had 127 terabytes of memory allocated. I don't understand what happens when you just have dereference address. You dereference address. It's an access to this address. The result is just not stored anywhere. If you would have local variable equals dereference address, it's the same, just you store the result then in a local variable. I didn't store the result anywhere. In the man pages, it says strategic calls to schedule can improve performance when high requested resources such as mutexes have been released. Why and when is it clever? Right after unlock? Yes, this can be useful, and we had an example like that in the code today, where we you remember the case where we had the while loop before, when we replaced the condition variables. We had this while loop where we just did a sem post and then sem wait right after one another. Using a scheduled there would improve the performance, because then you give other threads the opportunity to acquire this log. Otherwise, the chances are very high that by the time you do sem post, that the scheduling cycle is long enough that you also do the sem wait again, and then you hold the log again. So it then becomes basically a lottery whether you are stopped exactly between those two function calls. Okay. Will we get more hints for A3 in the next lecture? Maybe we will. So we will definitely work with Nmap, and I think that's helpful for A3, but also for A4. So that's definitely something. The next lecture will be on Monday in the regular time slot. We learn about Mmap in the next lecture, yes. We can use Mmap for A3, yes. Isn't it 2 to the 47 bits? I'm not sure at which point in the lecture we were here. That was 17 minutes ago. 2 to the 47 bits. 128 terabytes is exactly 2 to the 47 byte of memory. So it's not 2 to the 47 bits of memory. When allocating heap variables in A3, should we use mmap or malloc? The heap is organized with malloc, not with mmap. Mmap will allocate memory, but it's not heap memory, right? So let me check, but we just open the man page here and then say man mmap and search for heap. There's no heap, no mention of heap in the entire man page of mmap. Let's check for malloc heap. Oh, here it says heap several times. Okay, so mmap is not heap. Okay, let's hide this one again. Question regarding A2. If the locking is correct at the beginning of the program, first a hero gets created, then he goes to a country and then repeats this. Is this right? Or this is something to ask in the Discord, not for the lecture. Could you please paste your terminal inputs for htop, etc. you used in this lecture in the Discord server? I can add them as comments in the C files, and I will put the C files on my web server and link to them. Is this swapping? No, I can also show you that it's not swapping. You will be able to see that as well. htop. I don't have any swap file. So you see there's no swapping here, nothing. I don't have a swap file because I have enough memory in this system here. Okay. Where exactly can we find them then? In the C file? No, I will. So in the YouTube video, in the description of the YouTube video, I will add the link to the files, to the C files that I programmed. Next Monday, 10 to 18. No, I think there's a time. 10, 18. Ah, yeah, well, yes. That's Monday. That's 18th of October. Yes, exactly. Yeah. Yes, C files. Yes. C files. I will post the link here in the YouTube description and you can reach it there. It just takes me a few minutes after the lecture. Okay, with that, thank you for all the questions and for staying here. And I will see you next week in the lecture. Bye.